Hello everyone, my name is Mikola Servetnik. I'm from Foxconn Advanced Communication Academy, and today I'll present my work, which is called Performance Evaluation of Polarization Effects on 5G Cluster Delay Line Channels. I've done this work in collaboration with Weihan Xiao from Foxconn Advanced Communication Academy and Alisher Mukasha, who is a PhD student in National Jiao Tong University. Let me begin with the motivation for our work. First of all, antenna polarization offers extra degrees of freedom for MIMO processing, for example, for diversity combining or beamforming. The contribution of this work lies in investigating how antenna polarization influences overall link performance using the actual CDL channel models, which are proposed in recent release 15 of 5G New Radio. In our simulation results, we show performance gaps between different polarization scenarios, and it can serve a good reference design for future 5G communications. So let's do a small theoretical review on antenna polarization. First of all, the polarization of antenna refers to the orientation of electric field of radio wave with respect to the Earth's surface. Usually antennas are vertically, horizontally, or circularly polarized. Cross-polarization ratio is a ratio of the copolar component of the specified polarization compared to the orthogonal cross-polar component over the sector of beamwidth angle, or simply speaking, cross-polarization ratio is how much the wave polarization coincide with the antenna polarization. In our work, we consider two antenna configurations that act different in the polarization environment, as will be shown later. On the left side, we can see copolarized antenna arrays, so two parallel antenna elements, and cross-polarized antenna, which consists of two elements that are orthogonal to each other. As was mentioned in the motivation, in our work we consider CDL channel model. This is a 3GPP model for 5G new radio for wide range of frequency from 0.5 to 100 GHz, and it is a geometry-based channel model, and it's suitable for angle-dependent analysis, for example, for antenna array processing. This model incorporates a wide range of parameters and includes those of delay spread, delay values, angle spread, shadow fading, and cross-polarization ratio. On this slide, you can see 5 different CDL channel profiles uh, named A, B, C, D, E, and A, B, C, those profiles are concentrated on non-line of sight scenarios. Therefore, you can see that there is a lot of components at the delays after 1. And profiles D and E mostly concentrate on line of sight because the energy is mostly concentrated in the first tap. For the system model, we assume transmitter and receiver equipped with multiple antennas, and also we assume OFDM transmission so that the received signal can be written simply as channel multiplied with the transmitted signal plus noise. In our analysis, we focus on antenna array of size 2 by 2 to show those effects that come in by polarization of the antenna. And in first set of measurements, we want to show the received signal strength at each of the links H11, H21, H12, and H22. So let's take a look at the figure on the left. You can see 4 different figures, and figure represents the strength of the signal. So here is for H11, here is for H12, and so far and so on. We consider 3 different antenna configurations. First one with red is copolarized to copolarized antenna array. Second one is cross-polarized to cross-polarized, and third one is cross-polarized to copolarized. We don't consider copolarized to cross-polarized because that's essentially the same. So let us take a look at the top left figure. Here we can see that copolarized and cross-polarized antenna arrays have similar behavior with the maximum peaks at 0 and 180 degrees, while the lowest power is at 90 degrees, while cross-polarized and copolarized has opposite behavior because at 90 degree one copolarized element uh, is in the same polarization with the cross-polarized element. Therefore, if we look at the bottom right figure, we can see that the green curve behaves differently because at the same time when one element of copolarized array is in the same polarization with cross-polarized, another element of copolarized is orthogonal to it. Therefore, these two green lines are opposite to each other. Top right and bottom left figures can be explained with the same principle. So let us take a look at the right figure, which shows the aggregated power, which is sum of all the powers. And here is interesting result for cross-polarized antenna array. The sum power is constant. For cross-polarized, copolarized, it's nearly constant, while for copolarized arrays, the power is much higher than previous two. However, it falls down when two copolarized arrays are orthogonal to each other. That's why we can see a peak at 90 degrees. Therefore, we were interested to evaluate what effect does this received power difference have for traditional transceivers. Here in our work, we consider three state-of-art receivers. The first one is zero forcing equalizer, where we just invert the channel. Second one is MMSE equalizer, where we also invert the channel plus noise. And the last one is Alamudi transmission scheme, which is shown here and is kind of space-time coding. Here is detailed list of parameters which are set according to the specifications in release 15, particularly TR38901, and we consider 5 profiles for CDL channel, carrier frequency 28 GHz, and channel bandwidth 100 MHz. And for modulation scheme, we used QPSK, and we evaluated performance of co- and cross-polarized arrays for different MIMO schemes in terms of BER. So let us take a look at it. On the left-hand side, we can see BER for CDL ABC profiles, which are no line of sight, and the right side is D and E, which are line of sight scenarios. And there are 6 curves where the reference one is Rayleigh channel for 2x2 array, and the rest are different antenna configurations where we have for copolarized, we have 3 different lines. The first one is worst case, so when two copolarized array are orthogonal to each other. Best case, when they are have identical orientation, so slant angle has 0. And the last one is when orientation is uniformly random. And we compare it to different antenna arrays, particularly cross-polarized with random orientation, and cross-polarized co-polarized with, again, random orientation. So here we can see when two co-polarized antennas are matching their orientation, so the slant angle is equal to 0, the performance exactly matches Rayleigh channel. However, when the orientation is orthogonal, the performance is far away from original one. And for the random orientation, the performance is somewhere in between, which gives us the idea that basically for realistic scenario, the performance of copolarized array is going to be about 4 dB different compared to a Rayleigh channel, while the performance of cross-polarized antenna array is actually with random orientation is actually quite close to the Rayleigh channel performance. And similar situation is observed for line of sight. For MMSC receiver, the performance results have the same trend as the zero forcing receiver. So particularly for random orientation, cross-polarized array performs similarly very close to the Rayleigh channel, while for random orientation, copolarized antenna array performs much worse than its best case. Oh, and by the way, here on the line of sight, we can see that the performance of the copolarized array for the best orientation scenario for line of sight is still quite far from Rayleigh channel. The reason for that is that even for line of sight, there is still some cross-polarization ratio. So the arrived signal has different polarization angle from the transmitted array to received array. The results for Alamudi transmission scheme are slightly different from those of zero forcing and MMSC. That's due to the fact that Alamudi scheme is actually robust to the fading at single antenna. Therefore, we can see that for antenna array of cross-polarized and copolarized, it now matches the performance of the cross-polarized antenna array. The reason for that is that in case when polarization at one antenna of copolarized array, the signal is very low compared to another antenna, the Alamudi transmission scheme is still able to recover the transmission symbol during the second transmission interval. In the next set of measurements, we show how different antenna spacing affects the receive performance for CDL channel. So here we consider copolarized antenna array only, and we have different antenna spacing, 20 wavelengths to half of wavelengths. And we can see when antennas are more separated, the performance matches Rayleigh channel. This is explainable because when the antennae are farther separated, the correlation between two antennas become lower and lower, and therefore we can have the same performance as independent antennas. And in the next measurement, we show how the separation distance affect BR for different spacing. So we change spacing for step 0.25, and we can see that for different SNRs, actually antenna spacing plays a huge role in terms of BER, and that BER can actually jump in about half of an order when the antenna separation changes a little bit. This is again because of the correlation between two signals at the receiver, and when we change this separation, the signals become more or less correlated. Finally, I would like to conclude this work. First, through the extensive simulation, we now have evaluated the impact of channel polarization of the CDL channel model for arrays with copolarized and cross-polarized antennas on traditional MIMO transceivers. We have found that polarization causes 2 to 6 dB degradation for traditional copolarized arrays, while for cross-polarized arrays, this value is only 1 to 3 dB. So the final conclusion that cross-polarized antenna arrays are invariant to slant angle, and therefore it is able to provide better and stable QoS, and it is very likely to be used in 5G and R. Thank you for your attention. If you have any questions, please send me an email to address which is shown on the screen. And see you later.